Okay. And I'm going to use this that lets me go back and forth. So right now, I don't know where this goes. I've put it in several places. I don't know if it goes in a slide at the be in a slide ever. It definitely goes to remind us where we're headed. And
Mhm.
in the summary, I think we really want to actually say that. Um, so this is in there. So this is slide 18, which is, after the preamble, which we'll work on after we get the cherries and the narration for the cherries picked up, I guess, is probably the thing. What's next? Don't think we want to talk about that right now. I think what we want to actually do is what can we learn from one observation? And I have a title. Harold says, having trouble. Yay, Zoom. So say that we have this sample science project, and here's the title. Let's see what this has to say. Um, so isn't the one that has that. Okay. The hypothesis, not quite sure we want to say at that point. And the procedures sets up the context. The observed data for one observation per treatment group. This is height measured in millimeters on day 15 of the experiment. Height is a continuous variable since we could measure it with a ruler. We, earlier, I think we allude to categorical, etc., and that they can find out more about that uh, using the resources page. It really want to let them know these names, these words, but not go into it. So this is the quote homogeneous cherry. Let me see what the graph looks like. Okay. Um, I also have a note the same. All of our graphs need to follow all of our instructions in the first video, etc., that you don't present a graph without talking about at least what's there and probably even what is the result here because they have so few slides for the results. But
So I have a question here.
okay.
Are we showing this like it's an example slide then?
No, we're but we are uh, behind the scene doing that.
But my point is that this slide here is essentially the results slide from a fake slide deck.
Yes,
Okay.
um, that happened to use one observation per treatment group, and these are the heights of the bean plants. What do we say here?
Oh,
Uh, the vertical axis shows the observed height in millimeters measured on day 15 for each plant in each treatment group, as shown on the horizontal axis. The color of this symbol represents which treatment group. Each symbol is placed at the height of on the vertical axis corresponding to the height measured at day 15 in millimeters. So This is where, when you look at this, you suggesting that they pause the video and look at the graph and think about what info in the graph, what the info in the graph tells you about the effect of the different treatments. I'm not sure who would say this. The typical science teacher is going to tell you to show the mean and standard error of the mean. But with just one observation per group, you could only show the observations. It turns out Google chart will give you a mean for whatever that's worth. But the standard error and the standard deviation are not defined. These are measures of variability in plant height within each treatment group. But with only one observation per group, we we can't look at we don't see the variability. And this is the homogeneous cherry. We can come back to this. Um, so this is how I'm proposing to show that uh, you don't have a sums of squares. You don't have any degrees of freedom. You can't measure the mean squares because you can't divide by zero, etc. You can't get an F test. And what's probably more important is that the you you cannot evaluate the variance within the caffeine group or the coffee group or the water when you only have one observation at each of those. You have 2 degrees of freedom for between treatment groups, but 0 degrees of freedom for within groups. So we have no idea at all how accurate those individual data points are relative to whatever the true treatment effect is. You have no idea how far from the true effect these observations are. Whether you're close or whether you're far. So one of the things that we want to show as we go on. So let's look at this summarize. We'll come back to that. So n equal 2. This is again the homogeneous cherries.
Uh-huh.
Quite close.
Yeah.
And it shows up in the data, but there's amazingly enough. So this is how this will actually be shown. Here we are with 0.03, and this is the group I thought would be homogeneous, and it wouldn't be significant. So now
Oh.
let's look at last week's data.
Uh-huh.
You can see it's a bit differences about 20 within
Yeah.
each group. And this is the plot. This is the figure I think makes more sense to talk to when you're talking about how far apart that you can't tell how far apart they are, that sort of thing. Let me
Yeah.
see where that text is. I think. So this, can you see make this a little bit bigger? Come on. Well, that's not working.
Mhm.
learn how to get this to do what I want. There we go. So, somewhere we explained about the jittering. With n equal 2, you have a crude measure of the within group variability, but it's definitely crude and nowhere near the truth. When you have a big gap between two observations in the same group, so see now you would be pointing to this, which is certainly not as gappy as this. This is the slide that you would actually be using that text for.
Huh?
So let's pretend you're looking at that slide. When you have that big gap, we don't know if one of these observations in the caffeine group is an outlier. We don't know if the mean is being dragged down by this one or it's being dragged up by the larger one, as
Hmm.
there is more, there's, or if there's just more variability in response to caffeine. Here, with just two observations per group, the mean, by definition, is the value halfway between the two groups.
Yeah.
What happened to my text? Here we go. We also do not know what the coffee group, about the coffee group, because those two observations are closer together. We don't know if the coffee plant heights will all be close together, or we just got lucky to get these two that are the same height.
Hmm.
So then we really want to look at the summary table for the this is the whatever. And like trying to get it to have the p-value be non-significant made it worse. So that here we are at 0.07. Not quite sure what do you want to say about this, and this will be red. And you can talk about these aren't wildly different, but they're big.
Again, your average between the caffeine and the other two group is so big of a difference. It doesn't surprise me that it's starting to get towards significance.
Mhm.
It's so far away. The observed effect size is so large that it doesn't surprise me that you're getting something like that.
So if you were making a power statement and you aren't going to specify the magnitude of the effect, you can state it in terms of numbers of standard deviations. And if you only have two observations per group and what you see uh, is this big a difference between the groups, you have no better information. Is this true? Than to look at the analysis of variance.
Yeah, I don't know what else you would do.
Uh, repeat the experiment.
I mean, one of the things that I tell my intro stats class is that a lot of times when you're doing hypothesis testing, there's no need to do it. It's a duh, that's obvious. What you're actually interested in is how big the effect is, not whether there is one. Right? And for something like this, even at n equals 2 in each group, either something has gone horribly wrong with the caffeine group, or it's pretty clearly different.
I don't need to type this out because it'll be on the recording. Yeah. Oh, that's good. Yeah.
Right? And you can tell that with n equals 2.
Right. What you what you can't you what you don't have is a precise estimate of this effect.
Exactly. You have no idea whether this 30, 40, yeah, what is that? Like 40 point difference, 40 millimeter difference is
Uh-huh.
actually anywhere near the actual true difference.
And as you had said, you don't know whether something disastrous happened to the plants
Yeah,
in the environment,
exactly.
or whether there's that the caffeine really has that would have that odd effect if we repeated the experiment.
Yeah, I think that that's a good thing to point out with 2. With n equals 2, you're pretty sure that there's a difference at this point. But there's lots of reasons for that difference.
Uh-huh.
And you can't say that it's just because the caffeine retards growth.
Right. And you can't say, well, I treat them all the same. There's something that you maybe didn't control. Maybe somebody messed with your plants in between.
Mhm.
So I think we'll clean that up after and clean up those others. Um, so I'll summarize here what we had said in that, and then now let's look at two, three per group. We're not going to really want these essentially blank slides. Um, we're probably going to flash the procedure slide.
I think so. I don't think we need to talk about the procedure and talk about the graph every time. I think it's okay to say, well, now let's look at an example for a project that did 3 in each group. And just highlight that it's 3 in each group and make a note of that and move on.
Okay, and while we're here cleaning these things up, we need to say something about that the temperature it could vary with time, but it should be the same at a given time for all pots. And I fixed the dosing. Because 10 ml is about 3.3 ounces. That's from your your 3-in-1 bag for TSA flying. Um, so the real experiment, you had to mix a liter with it. So this concentration has to be the same, even if you only have one caffeine plant.
Mhm.
And so I'm getting around the not talking about how you dilute this. So you just make a liter of water with the 10-gram caffeine tablet every day. And you do this up to day 14, and then on day 15 you measure them. And here is the homogeneous data. I might have brought in the others and see how close these are. Let me zoom. Oh, good. Here's the last week's data. So this is you still have that. Let me see. Unfortunately, I put the text. Okay, so the homogeneous data had an awful p-value. This is this is the data that goes with the one with gaps, and it at least it's just 0.02. And the variances reduce here when you add the third, but when you get to five, it goes back up. Um,
Well, I think that's fair. It's not going to have a smooth path.
mm, because we're adding more variability when we add more observations.
Hmm. Well,
Okay.
it's not just that you're adding more variability, you're increasing the chance that something ends up wacky.
Ha ha! That's interesting. You're increasing the chance that you're getting more uh, comparable observations, but you now have three plants that can have things happen to.
Exactly. So it doesn't surprise me that it doesn't smoothly drop down because there's some randomness involved,
Right.
right? The idea is if you have 1,000 plants, something is almost assuredly going to happen to one of those plants, but you have 1,000 of them, so its effect is probably not going to be very big. Its effect on the mean and variance is probably not going to be very big.
Okay.
When you have three plants, if something goes wrong with a third of your observations, that's going to have a huge effect on your estimates of mean and variance.
Okay. So let's look at last week's data for three. For I meant five. So caffeine goes from 57 to 84. Will peak. So actually, I think to be consistent, these are all going to be 0001. So we still, actually, these variances are more comparable to the n equal 3 than to the n equal 2. So that's a little bit, that's better. Um, so some of what you were saying about 1,000 plants masking the effect of one wacky plant
Yeah.
goes here. And again, my plan is to have um, the two plots side by side with the caption down below describing what's in A versus B. Figure A, figure B.
Okay, there. Sorry, it was very slow. I saw A.
Yeah. What's interesting is now you have this, and you can actually see that this is pulling this mean up.
Yeah.
If this were not there, this would be would be down here. And this is pulling the mean down. This is the pulling the mean up.
Hmm.
But that's not enough. I have to touch it to make it show, I guess. Um, that's not enough to make them not have a difference. They clearly have a difference, which is not to say that it's caffeine necessarily, although it that sort of hits you between the eyes too. See, here's where you get the variance is larger, but I guess that probably um, the spread is larger.
Yeah.
Ah, that's good. I like that.
Yeah, we're finally starting to get reasonable estimates of variability.
Even though with variances like this for n equal 2, we're looking at that data uh, with uh, with trepidation.
Yeah, but the variances are noticeably bigger here, right? The variances were like 100 with n equals 2,
Um,
less than that.
this is
Yeah, with 3, you've got a 77 and a 90.
see, this is 239, 179, 137. This looks more like the n equal 10.
Yeah, but then you get to the third observation and it's like, hold on a second.
Um,
The problem is you have to cherry pick the large variance to keep it from becoming significant because the problem shows up when you're underestimating the true variance. Your points are far more standard errors away than they really should be.
when you're underestimating the true variance, so that spread is like 83 to 60. Ah, this is what's happening. Um, the the observation that I added is in the middle.
Hmm.
So I'm reducing artificially reducing the spread. The spread stays the same, but with n equal 3, now the variance appears to be smaller.
Yeah.
Okay. zoom down here. We don't want this one. So in summary, this is where we want to remind ourselves that we want those 3 points. Um, what can we learn with one observation? Do you want to put a sentence here that we can't learn very much at all?
I think in a summary, that would be a good thing.
And what can we learn by adding an observation? So we can actually now we can see the spread, the observed spread, but with only 2 observations, they may or may not represent what we would see. We don't know that our observations are representative.
Yeah, that's the thing. What can we learn with one observation? We have a very poor estimate of the mean.
Right.
What can we learn with two? We have a slightly less bad estimate of the mean and a very poor estimate of variability.
Meaning that there's no guarantee that the 2 observations we have are representative.
Yeah.
What do we get with 3?
Well, we have a slightly less bad estimate of the mean and a slightly less bad estimate of the variability. It just so happens that in this case, the variance gets pulled down because of that third data point.
Because of where that data point is.
Yeah.
Yeah. For the video, I actually think it would be interesting to have one of us ask the question and one of us answer the question.
I think that'll work.
Now, I'm also thinking at 3 to give numerical examples. We have an intuitive feeling after being statisticians for a while of what we mean by less bad. I don't think they have a scale for that.
Yeah. I'm trying to think about this because we've cherry picked it. We have the full 10 observations still, but we could say, well, what if it was this one observation? It could be this one plant instead, or it could be these 3 plants instead, right? Sometimes your data may look good like this. Sometimes your data may not look so good.
You want to show this graph when you're saying that?
Well, no, go back.
Or,
What I'm saying is go back to the two,
okay,
right? You had the one that was super significant because you massively underestimated the variance in one of the groups. And then you had this one, or are we still at, that's 3,
right.
right? You had two twos, I thought.
Oh, you like having 2 twos.
Well, I think that might,
That's fascinating. Yes, yes, great idea.
right? Because we're saying, well, look, it could be those two
Uh-huh.
where it is significant. It could be these two where it's not significant, right? And we've just added one extra plant.
Right.
We've picked one of the other 9.
Depending on which one you pick.
Yeah. right? But we know that we controlled all of this. We just arbitrarily picked two different of the other nine plants and got massively different results.
Drastically, zero point zero 0.07 versus zero point zero 0.03.
I mean, that's not a huge difference, but maybe we leave that toward the summary and say, well, look, what if you had those two instead?
Uh-huh.
Right? And you can show the two analysis of variance tables and say, look, the these are two experiments with the same plants. We just picked two different ones.
And then when you get to the third observation, you show the table for the third data set, because that's less than 0.0001.
Mhm.
So adding those two, what does that get you? So in this summary, we would compare cherry 1 to cherry 2 for n equal 2, and maybe even for 3, because it's where that third one falls that makes a
Yeah.
big difference.
Yeah.
And if you look at all 10 of them, you can see we had 8 observations to choose from. And that's about 70. We just happened to pick the one that was there. Look at the choices. Okay. So it I like having the data again when we're doing this. It lets us make some of the same points again with, and they can compare the two. I could even make this graph with 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're still losing somebody.
Mhm.
There's probably, yeah. Have to jitter them a bit more if I'm going to use the numbers. Or we can, you know, maybe I haven't put the raw data. But if we're only looking at the caffeine data, I can have the table of the caffeine data and show that. Okay. That's interesting. So going from 5 to 10 doesn't apparently change the p-value.
Well, I mean, it goes from vanishingly small to smaller. Look at how the F statistic changes. Right? I
Yes,
know the distribution of that F statistic also changes, but
55,
well, I guess
47.
not as much as I thought.
20. We could show them the F distribution for 2 degrees of freedom, 4 degrees of freedom. So when we're talking about, we need concrete visualizations to go along with the words, because the words mean something to us, that we need pictures that show them what those words,
Yeah.
examples of what they mean when we're saying that, you're getting a better estimate of something. What's that mean?
Yeah. That's really hard to convey in words.
And see, I think we're fighting the their first impression. As soon as that p-value is significant, that that's as many observations as you need. But uh, that's enough observations when you're 3 standard deviations apart. So, we need to show that.
Yeah. I mean, I almost want to do a variant on this video with a much smaller observed effect size.
That crossed my mind, that we thought, let's use that for a status set, but that data was generated with a big effect.
Yeah. I think the issue is that there's so much involved in the sample size discussion that you're right. As soon as you get to any discussion of significance, they're going to stop because it's just overwhelming. I don't know if we show the ANOVA tables then, or if we just show the summary tables.
I think it's cleaner for me to make another data set where we're just barely significant at n equals 10.
I think that's fair.
Because otherwise we're fighting something, that first impression when they see that even the 0.07 with n equal 2,
Yeah.
we've probably lost the battle.
Yeah. Again, the worry is that when we massively underestimate variance, we're massively overestimating how many standard deviations apart the means are.
Yeah.
And so even with something that's barely significant with n equals 10 in each group, you could still end up significant by chance at 2 or 3. All you need is one badly underestimated variance in the group that's actually different.
Well, this is by construction a problem with n equal 2, which is I can't have n equal 2 have the same spread that the n equal 10 has.
Yeah.
So all along, you're going to be underestimating. I mean, I can do pretend this is up and this is down. I could do this one and this one, but as soon as I add another point, I've decreased the variance,
Yeah.
which is what you want to do. I like talking to these graphs about where how what the effect is of where that third point comes from.
Yeah. The problem is, does it detract from the story? Right? I really like this discussion. I just worry that it's going to be hard for somebody that just wants a p-value to follow.
Maybe we don't want, maybe we want to make sure that we say that you actually want to look at these graphs, not just look for the p-value.
Yeah. Because again, when you have an effect size that big, you don't need a p-value except to appease somebody that says you need a p-value. Right? It's the that's obvious. Right? And it's a mistake that I know that I was guilty of back before I really understood this stuff. You just put your stuff into the software and it gives you a p-value and you say it's significant or it's not significant. And somebody who knows what they're doing looks at the graph and goes, why do you need a p-value here?
From my discussions with some of the board members, I know that a couple of them will like what we're doing with looking at where the observations, where the third observation is.
Hmm.
And I like your point that for some results, you don't need a p-value except for to give to someone who says you have to have a p-value.
Yeah. Right. I mean, that graph there is telling me more about the effect than the p-value will. I don't know how small the p-value is, but I'm pretty sure it's a small p-value when I see that the green dots and the blue dots don't even overlap. Now, if we only had n equals 2, I'm not so sure.
See, that's how do we tell them not to be sure?
Yeah, see, I think that's really hard
And see,
because there's an intuition involved,
it's
right?
not intuition. We think it's intuition because we've been doing this for 40 years, or 20 in your case, maybe.
But it's probably not even, well, maybe when you count all the experimental design stuff in grad school, maybe 20. But um no, I think what it is that we've seen enough data to have an idea of when the effect size is big, you need fewer data points to be like, yeah, that's something.
What's interesting is if we could get this graph with our low effect example when I regenerate it with a low effect.
Yeah.
Um, and in both cases, to to back up what you and I are saying that the three is not enough, is to show the graph with 10 and that you could have picked any of the other seven. And some of the other seven are going to overlap with the blue and the pink.
Yeah. Yeah, I think the other reason to go to a small effect size, number one, that's generally more reasonable. Number two, for the kinds of projects that they're doing, it wouldn't be unreasonable that they're searching for something with a small effect. And I don't know that we even need something that's significant at n equals 10. We just need something that's maybe like a p-value of 0.08 or 0.09 and say, hey, even with 10, we're not getting it, but a p-value of 0.09 that's, stronger significance than a p-value of zero point 0.4.
Um, what's interesting is some of the Westminster students, their projects, I think one, they were looking at the effect of temperature on the butterfly chrysalis, uh, and they tested huge temperature ranges. The low temperature was below 20 centigrade, and
Yeah,
the high might have been 30,
yeah,
35. Um, so what what happened is the temperature affected the development, which confounded the time to hatch, whatever the word is,
yeah,
because the temperatures were so extreme. But I think their advisors were probably suggesting to use 35 and 15,
yeah.
maybe 35, 20, and 15. Not sure about, some of the other, but that one I remember. Um, So you think I should aim for variances for the n equal 10 to get a p-value of 0.08?
Yeah, I think that would be a good lesson to say, hey, look, the effect that we're trying to measure here is small enough that even with n equals 10 in each group, we're not able to establish significance. One of the problems that there is with conveying the whole idea of significance testing, and it's something that I really struggle with trying to teach it to scientists, is the idea of the null hypothesis, because there is some effect. It may be a very, very small, negligible effect, but the idea that there's absolutely no effect really flies in the face of science,
Yeah.
right? You mean if I do this, it's not going to do anything. And it's really hard to convey the idea of the null hypothesis as kind of a mathematical simplification of the effect is so small that I don't care about it.
Well, you at the n equal 10, the 0.08,
Yeah.
um, the effect there is this issue of is the effect you're observing important enough to get sample size of 20 so that you get a p-value. Like switch back to confidence intervals. Dare we look at our confidence intervals?
I think we might even be able to look at the confidence intervals for just this big effect size, and that might show better than the p-value itself to say, hey, you know, yeah, we got a p-value of 0.03 or whatever, but look at our estimate of how much the caffeine is affecting the plant growth.
So I actually get that graph easily with the tukey HSD.
Yeah. I think that may be better because we can say, look, it's obvious even at like n equals 2 or 3 that either something went very wrong with the caffeine or caffeine has an effect. Our problem is we don't know how big that effect is. Look at our tukey post hoc confidence interval. I mean,
Yeah.
that thing's going to be a huge confidence interval at n equals 2.
Ah, I like that.
Right? I don't think it's worth fighting the this is significant at n equals 3. I think there's something to be said that there's an over-reliance on hypothesis testing for obvious effects when once you've established that it's obvious, the question becomes how big of an effect is there?
So are you backing off from having me generate a new data set?
I'm saying we might as well look at the Tukey graphs,
Okay.
and I think that that may be a better story
Yeah.
than trying to shoehorn this significant stuff in.
So Harold um, flashed on and off. He his Zoom
I'm
must
here.
be. Oh, you're
You
here.
you
How
don't
long
see
have you
me?
been here?
Oh, from almost the beginning.
Oh, good, good. What? So,
Well, I would like to put my vote in for confidence intervals, but just in terms of the ASA statement on p-values,
Oh,
that's
that's a good point, Harold. I hadn't thought about that.
uh, I've ignored that statement. Do you want us to reference that statement in our resources page? The
I
statement's
don't want to
been,
get things complicated, but I think um, I don't know if Tukey would take care of that, but
well, the
I think
2p per n equal 2 should,
But I was thinking error bars or something. Confidence intervals would work too.
Um, I like the simplicity of the Tukey plot. The error bars, um,
I think confident the ASA reference would be good for the teachers.
well, actually, with just the casual person who comes across our video, they can't. It's like giving a p-value when you don't need a p-value. If we have this in the resources page, it's taken care of. We're paying lip service to that. Um, but I much prefer confidence intervals, and I like the way the Tukey HSD plot. Doug Bates wrote the code for that. It goes all the way back to the white book. If you were you're not an S person, but um yeah, okay. So let's try to tell this story with that. And um we can decide when these confidence interval plots go with the individual sample size discussion or whether it's at the end. Harold, comments about, so we were at this, actually perhaps showing side by side the graph for n equal 2 and the graph for n equal 3. And what we would maybe be doing is the confidence intervals for n equal 2 versus n equal 3. Because what we're really wanting to show them is you've got these two observations and they're together sort of here, but the whole population of plant heights for caffeine has this spread, from 90 to 40. And if you have two observations with a spread that large, um, the estimate of the variance is huge. If you have two observations with a spread a third of that, which is possible because of where those 10 observations fall, you've underestimated the variance. And that doesn't mean anything to them, but maybe showing in the confidence interval, it gives them a visual estimate. What's fascinating is the concept of showing them something where the confidence interval looks small, but it's actually an underestimate.
Mhm.
So somehow, this first summary slide is slide 60, and we started at slide 18.
Well, again, that's because there's so many graph slides, and many of those slides in between we're going to replace with Tukey HSD graphs. It's a lot because there's a lot of graphs that are not going to take a long time to get through.
Right. So where I was proposing this, maybe the Tukey HSD goes with this.
Yeah. I mean, if you even want to go back to the original two and be like, hey, we achieved significance at n equals two because there was such a big difference. But look at the Tukey HSD. We're trying to now estimate how big of an effect the caffeine actually had, and it's giant.
The range is giant.
Yeah.
So I probably have the graph in the top left quadrant, the summary over here, and this down below. So it's not really divided into fours, but yeah. And these would all will still be together. And like you say, we're not going to, once we've gone over n equal 1 equal 2 and equal 3, we're not going to spend a lot of time. And we're actually going to be looking at the confidence interval plot. But
Yeah.
we're sticking all this other stuff there because we want them to get used to that your results include this type of information.
Yeah.
Okay, well, it's June essentially. It snowed in my corner of the San Gabriels yesterday.
Oh,
Mhm.
wow.
It's I actually it probably put my I have a really lightweight silk base layer that I put under my t-shirt, and on top of that I put a flannel shirt. And I have that combination on again uh, with my pajamas. And next Tuesday it's supposed to be 95 degrees. So we'll uh, talking about the variability. So what's your schedule next week? I have lots
Uh,
of work to do here.
well, I don't have jury duty next week, so that's good.
Oh, so you did your call in? You
I
didn't have
did my
to.
call in.
That's I was thinking of all the things you do, and going to stop the recording here. Um,